Project 1.5, the counting circuit. This here is the finished encased counting circuit. It can count up and down from 0 to 9, and the count is shown by the 7-segment display. To understand this build, some simpler circuits are needed that will eventually be built on to create this final circuit. The analog input is the first part of this circuit, and it acts as an input that starts everything. It uses the concept of low side switching, which dictates that the output will be high unless the button is pressed, in which case it will be low. However, since the output is connected to a NAND gate, the possible outputs are flipped, meaning that the output is now normally low, and when the button is pressed, it is high. This can be seen with the red LED. It is on because the output is low and it is connected to high. However, when the button is pressed, it turns off because there are now two highs. The NAND gate oscillator further builds upon the analog input. The output of the first NAND runs through a diode to a 10 microfarad capacitor and a 1 megohm resistor, both of which are grounded. These two components control the duration of the square wave created by this circuit and can be referred to as RC1. With more capacitance and resistance, there will be a longer duration and vice versa. As the capacitor slowly discharges, one input lead of the second NAND gate will be high. Because the other input is low, the output is high. This high goes through the 1 megohm fixed resistor to the 0.1 microfarad capacitor. These components can be referred to as RC2. When the current goes to the capacitor, it discharges towards the fourth NAND. This causes the fourth NAND to present low, allowing the LED to turn on. When the capacitor finishes discharging, it starts to charge back up, making the input leads of the fourth NAND high and causing the LED to turn off. Just like in RC1, the resistance and capacitance play a big role in RC2, as they control the frequency. If the resistance and capacitance are reduced, the clock frequency will be higher and the LED will flash more, and if they are increased, the frequency will be lower. The signal created by the circuit is called a square wave and is a signal that oscillates between high and low states. The 4017 integrated circuit, or IC for short, is used to divide the square wave created by the NAND gate oscillator. Though this chip has many useful pins, the only ones in use are the clock and divide by 10 output. The square wave is connected to the clock pin, where the chip then processes it and provides a square wave with a tenth of the frequency on its divide by 10 pin. The result of this in the circuit is seen by the speed of the count and can be observed through the LED. The 4516 is another IC in this circuit that is used primarily to count in binary, but also accounts for the reset button and the up-down slide switch. This chip takes the square wave presented by the 4017 and sends it to 4 different output pins, where each pin represents a binary value. With all its outputs, this chip can count using 4-bit binary values ranging from 0 to 15 in decimal. Here, the reset button is connected to low, and when it is pressed, it becomes high and resets the count of the circuit back to 1. The up-down slide switch controls whether the count is ascending or descending. When it is low, it counts up, and when it is high, it counts down. The final two components of this circuit are the 4511 IC and the 7-segment display. These two components work together to read and show the counting of this circuit. The 4511 takes the 4 outputs from the 4516 and gives 7 outputs that correspond to the 7 inputs of the 7-segment display. The 4516 reads the binary and sends signals to the correct pins so that a decimal number can be displayed by the 7-segment display. The binary values from the 4516 and their corresponding decimal values can be seen in this table. Both the button and the slide switch from the previous 4516 can also be seen in action here, with the button resetting the count on the 7-segment display to 0, and the slide switch changing the count from going up, back down. The final product of this project is the fully encased PCB version of the counting circuit. It has a switch that turns the circuit on and off, here a button that starts the count, and a switch that can change the count from ascending to descending, as seen here. Thank you for watching.